theoretical Thursday, but actually it's a Wednesday. Alright, so here we have our 500 gram mass, and we've taped with some clear tape a marker onto the bottom of the mass that we are going to include in the mass. And this will be our weight that oscillates on our bungee cord. Yeah, alright, it's going to oscillate on its own. And we're going to attach it to the string, pull it down, and then measure the period, and we can figure out the velocity at different points within the period, and we can get the amplitude, which is how high off of the natural spring length that it's going to be. Bungee is like a spring. So here this marker tip is going to touch a piece of paper that we pull along as this is oscillating up and down, and in pulling it along we should capture the sine graph and the oscillation as the energy deteriorates in this system. That's it.
That's it?
Yeah, we're good now.
Alright. Do you want to put it all the way up or do you want to put it down a little bit more?
Put it right about here.
Ready?
Wait, you're gonna pull it that way, right?
Yeah.
Okay. Try to get it so.
Alright.
Alright, ready?
Oh no, oh no, oh no, oh no,
No,
come on.
messed up.
Alright, let's do the trial again. Let's roll this off.
This is a physics Fred. Originally physics Fred was ordered a little differently. The marker was down here, and he was just the weight of the marker, and he wobbled. He'd wobble like wobbly. But thanks to a team of engineers, we developed a paper stabilizer. Now Fred's smooth. Doesn't wobble.
Obviously, as you guys saw in the video, our previous experiment was kind of a fail, and the reason was because we didn't have a stable base, and as Joe already explained, we use this plate to kind of stabilize it. And so now what we're going to be doing is we're going to actually be measuring the oscillation of the spring.
We've attached a marker to the top of the weight, and the marker is actually going to trace the position as the energy of our system decays, because this is called dampened oscillation like we talked about. So in dampened oscillation, the amplitude of each period is decreasing. So we're actually going to be graphing the cosine graph of position with our marker and show how it decays, and how over each, between peak to peak, is the same distance, because the period is the same amount of time, but they're going to get narrower.
Okay, so what I'm going to be doing now is, initially I'm going to attach Fred to this spring, and I'm going to see just how I'm going to measure the natural length that the spring extends, just based on Fred's mass. We're not going to add any extra force. It's going to be force due to gravity and Fred's mass. So we're going to make a line right here.
Yeah, so in our system now, this position becomes the natural length of the spring, which then Fred will oscillate around, as opposed to the natural length of the spring without Fred on it, and we've measured this already.
So it looks like this. This is Fred naturally. Now we're going to pull it down, and we're going to also make another mark on where we want to do it.
A little more.
Already?
Yeah, hold on, make the line.
Okay, no, this way.
Yeah, so this is our initial amplitude, A naught. Right.
And now,
is the timer ready?
let me just get it together. So now what we're going to do is we're going to time this. Okay, so we're going to time this, and I'm going to lap it every time it bounces down. So
Between where it starts down, then goes up, and then down once,
yeah,
is
so
one complete oscillation.
Yep, and it'll measure basically, it'll give us the data to get the calculations for the period.
Right.
And ready, set, you have any comments, Joe?
He wobbled. He'd wobble like wobbly.
Wobble dee wobble, I'm stacking my paper. My wallet look like a Bible. I got girlies half naked. That shit look like the
based on the data,
stuck at, like,
it's
1.1.
basically 1.1 seconds consecutively throughout the thing that it takes to go up and down, up and down, up and down to complete each oscillation. And now we're going to show you guys the chart, and Harrison's going to explain the chart.
Hey, how long have we been working on this today?
I think it's been 6 hours so far.
Yeah,
We came at 9, right?
right.
Almost 2, so 5 hours.
Thank God for
That's why we're
pizza.
enjoying pizza.
Hello. So today we are going to examine position as a function of time on this decaying oscillation experiment. So here we have the equation from the book, which is A naught natural log to the negative b times time over 2 times the mass times the cosine of the angular frequency over time. And we're actually able to determine this equation for the experiment we set up. So the first thing we did was take a look at our mass. We didn't have a balance, so we know that we can actually determine the mass if we know the spring constant of our spring. So to determine the spring constant of the spring, we had this chart here, and we measured the natural length of the spring hanging on the wall, and then added a water bottle, which we got 67 grams. Then we added 100 grams of water at a time, which is the equivalent of 100 milliliters, because 1 milliliter is 1 gram, and recorded the change in position caused by each addition of 100 milliliters. And as you can see, it's pretty constant. So from there, we put that in Excel, and this is force as a function of displacement. So here we have the length at each mass, and the force is the mass times the force of gravity. So force is increasing at a constant rate, and that rate is our slope of this line, which has a pretty good correlation, and our slope is 18.438, and that becomes our spring constant. So to determine our mass, we use the equation force equals spring constant times the displacement squared, and we know our spring constant now, and then we measured delta x on this graph, which is that green line on the side there. That's 28.1 centimeters. So that's the length off the natural length that when we put Fred onto the spring, Fred displaced the spring that much. As you can see, it's going to be just over 467 grams, somewhere over there. And actually, when we calculated it out, it's 0.544 kilograms. So pretty close there. The next thing that we derived from that equation was the angular frequency and the period. So angular frequency is 2 pi over capital T being the period. So here we have 8 different periods, and a period is 1 oscillation. So we pulled our mass down, so it's from trough to trough. And we used the lap function on the iPhone to record the time for each period. Then we average those to get our T average, which is 1.03 seconds. And actually equation 1311 in the book is T equals 2 pi times the square root of mass over the spring constant. Using that equation, it's 1.07 seconds. So really within error, we're pretty close. The next thing that we looked at and measured was A naught. A naught is the initial amplitude. And if we look on our graph here, the initial amplitude is how far we pulled it down. And that is 22.3 centimeters. So we pulled Fred down to about here and then let him go. The next thing is the angular frequency, which, like I said, is 2 pi over t, and when we calculate that out, that's 6.1 radians per second, and radians can cancel out. So we go now to that equation for position as a function of time, and now we have everything. We have A naught, we have B, we have our mass, we have our angular frequency, and now we just need to plug in a time. But we go about finding B. Actually, we don't have B yet. That's what we're doing right now. We don't have B, so we can rearrange this equation, and we take the ln of both sides, and the what e is raised to comes out in front then, and the ln of e is just 1. And we isolate B, and we did this for several different times, and we got a B average of 0.12691. Now we're gonna test this out, because that equation that we got, now that we have all these missing parts, that should give us an accurate position. So at 1.35 seconds, we plug that into the equation here, and we get 0.189 meters. And at t equals 135 seconds, we actually measured that height off of the x-axis here, and got that to be 18.8 centimeters. So we're within, a thousandth of a meter, which is pretty good. Now the next thing we can look at here is velocity. And we know that from calculus, velocity is the derivative of position. So we're going to let that complicated thing in brackets be equal to a, and then we're going to take the derivative. So the derivative of x equals the derivative with respect to t of a cosine wt. So here, by the chain rule, we can bring a out in front, but then to take the derivative of cosine wt, the derivative of cosine x is negative sine x, but because w is multiplied by t, we need to bring that on the outside as well, and we result in velocity equals negative a sine of the angular frequency times the time times the angular frequency. And for our system, we plug back in that nasty thing in brackets, and we get this for our velocity. Alright, so what we have just proven is that velocity is the derivative of position. And since velocity is the derivative of position, we know that velocity is the slope of the line tangent to the graph of position at a given time. So what we've done here is, at a time of 1.575 seconds, we've actually drawn out the tangent line there and picked 2 points on it to get a change in y and a change in x, and we can calculate the velocity, which is the slope of that line. So here, velocity equals the slope of the tangent, and velocity equals change in position over change in time. We measured change in position, which is 0.165 meters. That's this green bracket here. And then we convert our measurement for the x component of that triangle, which we know is 0.09 meters, and we multiply that by 0.9 seconds, which is our t for this period, divided by 0.49 meters, which is the length of the entire period. So here, if you see on the top of the page there, from this trough to this trough is 0.49 meters, but it takes 0.9 seconds to go that 0.49 meters. So as a fraction, that gives us, for that little piece on the triangle here, it takes a fraction of 0.9 seconds, and that is 0.1653 seconds. So then velocity equals 0.165 meters over 0.1653 seconds, or 0.998 meters per second. the next thing we did, now that we know velocity, is assuming that the top of the peak there, that would be the maximum potential energy of the spring. And at the point of inflection, where we measure the velocity, that is where potential energy equals 0, and where kinetic energy is at a maximum. And theoretically, potential energy initial should equal kinetic energy final. So here's what we do. At a time of 1.35 seconds, which is the time of that peak, we have 1/2 k times delta x squared. We know our spring constant. And we also know our delta x, which again is 18.8 centimeters. So this gives us 0.325 joules. We just determined the velocity and we plug that into the equation for kinetic energy. We know the mass is 0.544 kilograms, velocity is 0.998 meters per second squared. But that gives us 0.221 joules. The simple answer lies in non-conservative forces. UI equals work lost plus kinetic energy final. 0.325 joules equals work lost plus 0.056 joules. Sorry, that should be 221 joules, and that gives us 0.56 joules is the work lost. Now we can look at this in terms of percentage. Energy lost due to non-conservative forces would be that number of joules lost over the U initial times 100, and that's 16.8%. Now we did this and calculated similar numbers for a number of different points of inflection. Alright, so finally we're going to look at change in velocity over the time in the system and loss of energy over the entire system. So if you look, here's our start. The amplitudes of each period are slowly decreasing as the height, narrows down to the end of our graph here. And what we look at also is velocity. So velocity at this point here is what we calculated originally. That's 0.998. Then we go to velocity here. That's 0.94. Then velocity here is 0.745. And the final one we calculated is 0.585. Now we skip velocity here because on the top here you have the period. This is 0.49 meters covered in 0.9 seconds. This is 0.53. This is 0.42. This 0.42 here, as opposed to 0.5, 0.53 again, is when we got stuck pulling it. We got hung up, which caused a distortion in data, and the velocities do not match the trend. But the general trend from here to here to here to here and continuing is decrease in velocity. The other thing we look at is potential energy. And U here at this peak is 0.325 joules. At this peak it's 0.292. At this peak 0.171, and at this peak 0.116. We also calculated kinetic energies at all these points, and again those are decreasing too. And like we said, at this peak here with the 18.8 centimeters, our percent loss in energy is 16.8%. At this peak, we calculated kinetic energy too and determined percent loss in the same manner, and that is 14.7%. We did the same thing here. We got a 12.2% loss, and finally an 18.8% loss. Now, these numbers may appear all over the place, but given the amount of error in such a raw experiment like this, they're really within a few percentage of each other, which suggests the nature of that constant B that we looked at. In this system, there is a decay constant because our energy is being lost at a constant rate. It's about the same percentage loss over the whole time of the system that we looked at. We can even show this graphically if we look at the velocities and the steepness of the slope. We know that velocity is slope and velocity, the magnitude, is decreasing, but we can illustrate this graphically as well, or I should say visually, if we set up some tangent lines here. At a couple different points to help show what we're talking about. So here we go. The first one has the steepest slope, and it's gradually decreasing over time. If we laid a fourth one out there, it would be even less. So in essence, what we've just proved is that not only is the derivative of position velocity, but that velocity, kinetic energy, potential energy are all changing over time at a constant rate due to non-conservative forces in this system, which in this case is the force of the friction between the paper plate that Fred's attached to and the paper that we pulled behind it. And that would be our Theoretical Thursday. Thanks for watching. We deserve an A for the damage we're doing to Hassan's wall. End of story.
It's amazing, I'm the reason everybody fired up this evening. I'm exhausted, barely breathing, holding on to what I believe in.